So I think we can start as people. Well, I'll just wait for you to get set up. But thanks for coming despite the rain. Very much appreciated. Um, yeah. So today we're recording. Yes. So today we'll be doing some exercises from problem set 3. But before we do that, I have two announcements. So the first one is in relation to the bonus assignment. So I don't know if you remember, but at the beginning of the semester, a very long time ago now, it was announced that there would be a bonus assignment. So the bonus assignment would essentially just count as a bonus to your final grade. So it still exists. I've finalized making the bonus assignment. So we've decided for it to count for plus 3% of the final grade. So if you get the whole bonus assignment marks correct, then you get plus 3 on your final grade. So that's kind of nice. The content is going to be on a bonus sort of content known as learning automata, which is essentially when you're given some number of strings which are and aren't in the language, and you kind of want to find an automata that can sort of be explained by those observations. So it's kind of like the reverse process of what we've been doing so far. So I'm going to post videos related to that. I'm going to post videos, and then the bonus assignment is just going to be about trying to replicate the algorithm. So it's actually going to be quite straightforward. So it should be like an easy, very gettable 3%. So that's the first thing. The other thing is that my office hours have changed to Wednesday from 12:30 p.m. to 2 p.m. So no one was really coming. I think it was because they might not have been conveniently placed. So I've changed them to this time, exceptionally for tomorrow. So tomorrow my office hours will still be, for this week, they'll still be on Friday, but they'll be from the same time, but just on Friday. So 12:30 to 2 p.m. So this is going to be, tomorrow it's just going to be via Zoom. And for the rest of the semester, it's going to be hybrid. Okay, so you can join via Zoom or in person. Okay. Okay, cool. So yeah, so like I said, today we're going to do some exercises from problem set 3. In particular, we're going to start with context-free grammar exercises. So there's a couple of things that you can be asked in a context-free grammar exercise or question. One of them is essentially, create a context-free grammar such that, dot, dot, dot. So that's going to be most of what we're going to be doing today. You could also be asked, given a context-free grammar G, what is L of G? So this could be another question that you're asked. And then the third type of question is like a conversion type question when you're sort of asked, convert the context-free grammar G, to something where the something is maybe like an ambiguous grammar or in Chomsky normal form, something like that. Okay. So for this stuff, we're going to do this next week, actually. Okay, so today we're going to do context-free grammar exercises of type 1, and we're also going to do PDA exercises of kind of the same type. Okay, so the first question that we're going to do is, like I said, from problem set 3, it's question 1, A. So sorry, today I didn't have the time to print the problem sets. I'll do my best next time, so you can have it. Essentially, the questions though for question 1 is just create a context-free grammar G that generates the following languages. And the first one is A star, B star, okay? Okay, so how could I do this? Well, let's first think of like, what are the strings in this language? The strings in this language look something like, some number of A's and then some number of B's, right? Those are the strings in A star, B star. So then you might be tempted, right? You might be tempted if you want to create a context-free grammar to generate this language to do something like, oh, well, I have my start variable, then from my start variable, I'm going to start generating a bunch of A's, right? And then at some point, I'm going to stop and then start generating a bunch of B's. And then at some point, I'm going to stop generating the B's and generate the sort of base case, right? So I could do something like this. And this would indeed give me something like, I could very doably generate something like, a cube b square. I could generate the first A with AS, then some other A's with, again, this production rule. So I could get to something like a cube S. Then at this point, I could switch to generating B. So I could get a cube BS. And then I could do an extra one. I'll just write it. I could generate an extra one and get a cube B square S, and then end and get a cube B square. Right. So I can definitely generate all the strings in A star B star. But if I want a grammar that generates exactly this language, this grammar is not going to work. Why is it not going to work? Yeah. Yeah. Yeah, exactly. Yeah, very good. Yeah, so the answer to the question I just asked is, yeah, it doesn't really work because in this case, I've created a grammar G such that L of A star B star is a subset of L of G, right? So there's stuff in L of G that's not in L of A star B star. For instance, using this grammar G here, so let's call this G. Using this grammar G, I can generate something like a BA, right? So I can start with S and then generate a B with BS, and then replace the S with AS, so I get BAS, and then terminate, so I get BS, right? And BA is not in L of A star B star, so that doesn't work, right? Because what I want is an equality. Can anyone tell me what actually L of G generates? Yeah. Yeah, yeah, exactly. So L of G is actually L of A or B star, right? So in other words, it's any string over the alphabet AB. Why is this true? Because, consider any string over the alphabet AB. So, that string will be something like sigma 1, sigma 2, dot, 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 sigma n, right? Well, I can generate this with my grammar G. I can generate this with my grammar G because I can say, okay, I'm going to start with S. And then for this first sigma 1, if it's A, then I'll use AS. If it's B, then I'll use BS. And then I can just repeat this for all the other letters in here. So I can generate any string over the alphabet AB, right? So that's not quite going to work, right? So instead, what it seems like I kind of have to do is I kind of have to constrain my grammar in some way, right? Because what I kind of want to do is, if I want to create a grammar G prime that actually works, I kind of want to make it generate the A's first, and then stop generating the A's and move on to generating the B's, and sort of prevent my grammar from ever going back and generating more A's, right? So how am I going to do this? Well, I just have to sort of split my grammar into two kind of levels. So I'll first start by generating the A's, right? So I can say, let's generate all of the A's first. So I can get, S and then AS and then AAS and then any number of A's. And then at some point, I'm going to stop and move on to generating the B's, right? So at some point, I'll have a pipe, right, to suggest that I can also at some point move on to the variable B, which will be responsible for generating strings of just B's, right? So that'll require me to have something like B, right? So then I can do something like, S gives me AS, and then using any number of derivations give me any number of A's and then S. At some point I can swap and get A, then B, right? And then when I'm at B, now I can start generating a bunch of B's, right? But I have to be able to sort of end this process. And to end this process, I need one final production rule, which is going to be what? Yes, B gives me the empty string. Nice. There's another way of doing this. Can anyone see the other way of, yeah? Yeah. Yeah, so I think I didn't hear you, I didn't hear everything you said, but I think what you said is something like you could do S gives me AB, and then you could say, well, A could generate a bunch of A's. and then B could generate a bunch of things, right? No, that's not what you said. Oh, meaning A and B. Oh, but then A and B that forces you to let's say this or this or this. No, I don't think that's gonna work. No, no, because then you get the same problem as as here, I think. Um, I'll have to think about it. Let me get back to you. I have to think about it. Yeah, question. Yes, you can terminate. Yeah. So the question is, why is there not an epsilon here? I mean, there could be, but it's not necessary because you could just transition to the B and then the B can just generate epsilon. Yeah. 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 So they're like the suggested, so this is G double prime. The suggested G triple prime is S. So I'll have to get back to you. I'm very bad at thinking on my feet. Um, so I'll check just to make sure that it's good. Yeah, maybe. I don't know. I have to check it. Sorry. Yeah. It's a bit hard for me to think on the spot. Okay, good. Great. So that's for question 1A. Let's do question 1B. The question 1B is to generate a language, to create a grammar that generates the language UAWB, where UW is in AB star, and then U, the length of, or no, sorry. Yeah, the length of U is equal to the length of W. Okay, so I'm actually going to give you some time to do this one, but let me just sort of explain in general what the structure of this language is, right? So I have strings, right, that look like something like some string U, and then the letter A, and then some string W, and then the letter B, right? Where the length of U is the same as the length of W. So like so an example would be something like ABA, and then BVAB, right? Because I have, U is ABA, W is BBA, and then I have my A in the middle, and then my B on the right, okay? So this is the general structure. So I'm going to give you a good amount of minutes, let's say 3 to think about it. And I will walk around in case you have questions. Okay, I'll also close the door. Yeah, I do. If you're done, you can just let me know and I can talk to you personally. Yeah. Mhm. Yeah. Yeah. Okay. So you have had some time to think about it. Let's think about it together now, collectively, as one. So, how can I do this? Well, essentially what I can sort of do is I can kind of identify that there's basically two main components-ish to this string in general. I have this part of the string that kind of requires a matching here, although it's not really a matching of the same letter. It's just that it's a matching to sort of ensure that the lengths are the same. And then I just have like this sort of dangling B here. So I kind of know how to do something like a matching of letters because that's kind of like A and B N, right? So the logic is going to be to kind of do something like A and B N here, just to do the dangling B at the top level, and that'll be the grammar. So what is this going to look like? If I start at S and I get something like, let's say A, B, so B will be there to generate B, and then A will be there to generate kind of from one side and the other of this A, any combination of pairs of letters, right? And because the alphabet is of size 2, then there's like 4 possible combinations, right? There's, A with A, B with B, A with B, and also B with A, right? And if like, because I have the strings being arbitrary, I don't care what the exact letter is as long as I can match them in terms of the length. So that's going to look something like A, so that's the first kind of matching, then B, A, B, so B, A, B, then A, B, and then, it's not here, but you could imagine that I had something like B and then A here, right? So it could be B and then A. So, okay. And then how do I sort of end this generation was my base case. A, right? Yeah. So at some point I have to kind of stop doing this matching because at some point I want to generate the midpoint, which is A. So at some point I'm going to stop and generate A. Okay. Any questions about this? Yeah. Then it's not context free. Yeah. And you can't do it. Yeah. So the question was, what if it was U, A, U, B? Then have you seen the pumping lemma yet for context free languages? Oh, it's today? Okay, then you can use the pumping lemma for context-free languages to show that this is not context-free. Yeah. Okay, nice. Any other questions? No. Okay, doesn't look like it. All right, let's do question D. So question D is the language. So I want to create a context-free grammar for the language uh, which contains strings of the form V, W, V, W, R, where V and W are both in AB star, and where the length of V is exactly 2. So what are these strings in L going to kind of look like? They kind of have two characteristics, right? The first thing is that there's kind of this VV thing, right? So, and this V thing has to have a length exactly 2. So the first observation I'm going to make about L is that there's kind of like 4 cases for the substring V. So there's 4 cases. In particular, V could be AA, AB, BA, and BB. The second observation is that this kind of part here is a bit of a reminder of like palindrome, right? Because you have like W and then W reverse. So if you have something like that, right? If you have a string like W, W reverse, you know, an example would be something like ABB. And then if I take ABB, I reverse it, I get BBA, right? So altogether, this is a palindrome, right? Because from left to right, it's the same from right to left. But in particular, this is a palindrome of even length because the length of W is repeated twice. So it's of length 2W. So these are even length palindromes. And in case Jérôme didn't show you, there's like a kind of formulaic way of generating palindromes of even length. So how do I generate a palindrome of even length? Well, I just make the observation that, you know, palindromes, essentially, it's like they have matching leftmost and rightmost letters, right? So the leftmost letter here is the same as the rightmost letter here. The second leftmost letter here is the same as the second rightmost letter here, and so on kind of recursively, right? So to generate even length palindromes is something like S gives you ASA or BSB or the empty string, right? So this is kind of the second observation is that, you know, this thing kind of reminds me of this thing, except that now I just have a V here, right? Okay, so it seems like I can combine these two ideas together. Let's try to do that. So the way that I'm going to try to combine these two things together is I'll say, well, my top level start variable production rule is going to be S gives me X and then P, where X is going to be for generating any of the 4 cases. I'm going to have, you know, X could be AA or AB or BA or BB, right? And then this P thing is going to be for like the palindromic thing, right? So I'm just going to reuse this kind of idea, but instead of the epsilon, I'm going to have X as the kind of base case, right? So I'm going to have P gives me APA, BPB, and then X, right? Okay. So there's a problem with this grammar, right? What's the problem with this grammar? Yeah, yeah, exactly. Yeah. So just because I've named X and X, right, here, doesn't mean that when I use the X in the different parts of the derivation, it's going to go to the same thing, right? So this is a very sort of common misconception is, you know, if I have the same variable somewhere, then it's going to give me the same thing as when I have it later. But this is not the case, like I can show you. So if I take a parse tree derivation, let's see, I'll have X, S gives me XP. Let's choose like X gives me AA for this left X, so I'll get AA here. Then let's generate like the sort of palindromic recursive case. I'll get A, P, A, and then B, P, A, or sorry, B, P, B, pardon me. And then let's do the base case. So I'll do P gets replaced by X, okay? But at this point, right, there's nothing forcing me as like the generator of the context-free grammar to do the same thing as I did here. So I'm very free to do, you know, X gives me AB, right? In which case this kind of violates the structure of the language because the structure of the language is VWVWR, right? So that's kind of a problem. So can anyone think of a fix of this? Yeah, nice. Yes, that's right. So the sort of trick to avoid this, right? To avoid this, you essentially need to hard code every single like possibility, right? To avoid this, hard code every single V, every single instantiation, let's say, of V. So what I mean by that is, you take the form VW, VW reverse, so VW, VW reverse, and then you just replace it like 4 times, once by AA, right? So I'll get AA, W reverse. I'll do the same thing for AB, the same thing for BA, and the same thing for BB. So I get 4 different cases, right? And now I can just get my grammar to generate each of these cases, right? So that's what I'll do. So I'll do S gives me AA and X1, or AB and X2, or BA and X3, or BB and X4, right? And then each of these guys is going to correspond to like the corresponding palindromic thing, right? So I'll just do the X1. So X1 is going to be, A, X1A, or B, X1B, and in this case, because like I know X1 is next to AA, I'm going to just use X1 gets replaced by AA. Okay, and I'll let you do X2, X3, and X4, but it's basically the same thing. Okay. Cool? Nice. All right. So the last context-free grammar, yeah.
Then he was fixed.
Ah, yes, very good. Yes. Yes. Yeah, good question. Yeah, so the question here was, what if V is not bounded, right? So what if I have, V, yeah, VW reverse, but V now does not have a bound on its length, then yeah, it's not context free. Yeah, then it's not context free. In fact, in general, whenever you have like a duplication of a string, unless there's like some like nice thing about the language that allows you to sort of simplify it, it's not context free. You just can't do something like WW with a PDA or a CFG. Yeah. The interesting thing is that it's not true for, so WW, so I'll just, this would be a very long tangent, but WW is not context free. But actually, the complement of L is context free, which is a bit surprising. L complement is context free. So this is actually a very difficult exercise. So I won't do it here, but I'll leave it to you to ponder about as a difficult exercise. As a difficult. Okay, nice. So let's do one last context-free grammar exercise. This one is question 1E, where we're looking at the language W in A, comma B, comma C star, where the number of A's in W plus the number of C's in W is equal to the number of B's in W. Okay, so this is the language. What are some strings that belong to this language? Well, something like, I don't know, A, B, C, B. This is in, let's call this L. This is in L because I have 2B's and then 1A plus 1C, so 2A plus C's. So I have 2 is equal to 2, right? So that's in L, but something like AAC, BB, this is not an L because I have 2B's, but I have 3 A's plus C's together, right? So this is the language. Now, it's kind of actually a bit difficult to think of a grammar because there's no restriction on the order, right? So like this is valid, but also like if you reverse this, it's also valid. If you swap the first part with the second part, it's also valid. So you have to consider like all possible combinations. That's a bit tricky, right? And so to help you out, let's think of like slightly more simple language before we actually do this one. So before doing L. Let's try L prime, where L prime is just over 2 letters. Okay, where I want the same thing. I want that the number of A's is equal to the number of B's, right? So this is like a bit easier, and then we'll see how we can generalize. Okay. So how are we going to do this? The trick is kind of a clever one. It's to kind of try to represent the string based on its recursive structure, but in a very specific way. So what is the specific way? Let's look at a particular example. So I have W is AB, BA, AA, BA, BB. So this is definitely in L prime, right? Remember, we're doing L prime just because it's a simplified version of L for now, right? So this is in L prime because I have 1, 2, 3, 4, 5 B's, 1, 2, 3, 4, 5 A's, right? Now the trick for these types of languages is to consider a plot, which kind of comes out of nowhere, but it's actually quite a nice idea. Where this plot, I'm going to plot the difference between the number of A's and B's with the y-axis. And I'm going to use the position or the sort of index of W as the x-axis. Okay? So why is this going to make sense? Because the thing that's going to be nice is that if I kind of like plot NA minus NB with this with these two axes, what happens is, if I have this first A, then my line is going to go up, right? Then with this B, my line has to go down, right? With the next B, my line is going to go down. The next A is going to go back up. With these two A's, I'm going to go up twice. This B, I'm going to go down. This A, I'm going to go up. The two B's, I'm going to go back down. And if the string is truly in the language L prime, then at the very end, right, I'm going to go back to like y is equal to 0, right? So why is this nice? Because now it sort of seems like the recursive nature of the language has kind of appeared in a bit of a more explicit manner, because it looks like, this first part is actually a string that has the same number of A's and B's, right? And this string as well, and this string as well. So that means that what I kind of want to do at the beginning is I just want to identify each of the substrings and then generate them from there. So what I'm going to do is first do that using the production rule S gives me SS, right? So S gives me SS, that's going to allow me to do something like, well, here I identify 3 substrings, so I get something like S gives me SS. Let's do leftmost derivation, so replace the first S with SS, so I get SSS, right? Now, at this point, I'm ready to do the sort of matching for each of the substrings, right? And how do I do the matching? Well, I just observed that, if in this subplot I go up by 1 at the beginning, then at the very end, I have to go down by 1, right? And going up by 1 here means, producing an A, and going down by 1 here means producing a B. So that means that I also need S gives me A as B, right? And the nice thing about that is that, it's kind of like, if I do this A as B, then, maybe for this one, it's as if I'm like moving my x-axis up. So then I get like 2 new recursive cases that I have to do, right? And that's nice, because I can just reuse this thing. The other case is, if I go down instead. Well, if I go down instead, then I produce a B to go down and then an A to go back up. So I get S gives me BSA. So now I have these 3 production rules, which are like the sort of workhorse. Now I need the base case. What's the base case going to be? Empty string, yes, exactly. Why is empty string the base case? Because it's the simplest string that has the same number of A's and B's, in particular 0 A's and 0 B's. Okay, so this is a context-free grammar. There's actually a slightly different way of designing it, but this is one way of doing a context-free grammar that generates L prime. Okay, now as an exercise for you, I'll give you like a couple minutes. How can we sort of generalize this? So how do we generalize this idea? to the number of A's plus the number of C's is equal to the number of B's. Okay, so I'll give you 2 minutes. And yeah, feel free to yes, it's very, very simple. Yes. Some might say it's the same homomorphically. So yeah, let me know and I can oh,
You on it to the state. Yeah, it's like it's a pipe. Okay. And purpose. Uh, yeah. The purpose of finding the object shouldn't not be financial. So there's finding three items under rule, doing some well operations. Think about it. Yeah, think about it. Yes. Oh. Yeah. Exactly. Yes. Very good. Okay, 2 minutes. Wow, that was fast. Okay, so hopefully that was enough time to think about it. So essentially, the idea for how we could generalize this to 3 letters is essentially you kind of just want to treat A's and C's the same way. Basically, they're kind of like the same letter, right? That's going to be the general idea. So, you could imagine for this plot, instead of NA minus NB, it was as if you had NA plus NC minus NB, right? So how do I do this? Well, I, still have my top level S gives me SS, but then for ASB, I'm going to have instead X SB, right? And then this X is going to be either A or C, right? And then I can also have B as X, where X can also be A or C. And then I'll have my base case epsilon, right? So essentially, it's the same idea, right? If I see an A or a C, I'm going to go up. If I see a B, I'm going to go back down. So it's the same logic, right? So then this is the sort of generalization, right? And in general, you can maybe see how you could do this for like an arbitrary number of letters on the left and the right of the equal. Okay, cool. Any questions about this? No? Okay, all right. So let's move on to exercises about PDAs. So PDA exercises. So for the exercises about CNF and CYK, I'll do those next week. So CNF plus CYK exercises will be next week. Okay, so what are the types of PDA exercises that one might stumble upon in the wild or in Complete 30? One of them might be, design a PDA. Typically, you can assume that it's an NPDA, which accepts via accept state or empty stack, such that dot dot dot. So that's one typical question that you might get. Another one would be, something like given a PDA M, what are some like properties of L of M? So what is L of M? That might be one. Okay. And then a last type of question you might get is something like, convert a PDA to a context-free grammar. So what you saw today, right? Hopefully show you that today, right? Yeah, skeptical nod. Okay, shrug, skeptical shrug. Okay, so for the purposes of this tutorial, we're only really going to do questions of type 1. Okay, so let's do a first one. This first one is going to be, quote unquote easy. Maybe it's not easy for, yeah, let me stop talking. Let me stop qualifying the question. So the first one is actually not from the problem set. It's going to just be the question I gave at the end of lecture 13. So this is uh, from lecture 13. So at the very end of the lecture, I said, we could create a PDA for this language using the conversion algorithm. But in this case, what I want to do is I want to create the PDA kind of directly, right? So the question for all of these exercises is going to be, create an NPDA either via accepting via empty stack or accepting via accept state such that it accepts L, right? So that's the question. Okay. So now the question is to do this for the L here. So how are we going to do this? Well, remember from lecture 13, we sort of observed that this language is kind of a union of two languages, right? So what we kind of need to do is design PDA M1 for L1 and another one M2 for L2. They're going to be different because like the logic here is different, right? Here it's that you have something like AA and then B4. Here it's like you have an excess of A's, right? So clearly the logic is not quite the same. And once I have the machines M1 and M2, I can just join them together like I kind of did for NFAs with epsilon transitions. So the way that works, if this is M1 and this is M2, right? Then the way that I can join two machines together with epsilon transitions for PDAs is I firstly have the epsilon transition for what it reads, but also the epsilon transition for what it does to the stack, right? So this says, read nothing, and this says change nothing about the stack, right? And then I would do the same thing for this guy. So read nothing and change nothing about the stack. Okay. So now let's do machine for L1 and L2 respectively. So for L1, I have AN B2N, right? So what's going to be the idea here? So essentially what's going on is, if I have the string AA, B, 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 right? Then, this is kind of similar to ANBN. So I probably want to do something like, push when I'm reading an A and pop when I'm reading a B and ensure that at the end my stack is empty, right? But now it's not, for every A push 1 and for every B pop 1. Instead, it's going to be for every A push 2 and for every B pop 1, right? So why is this going to work? Because if that's the logic, then, if for this first A, I start with an empty stack. Let's assume it has a not at the bottom. For this first A, let's add, 2 X's, right? For the next A, let's add another 2. So now at this point, right, I have 4 X's on my stack. I transition to like popping an X for every B that I read. But now what's going to happen is the only way that I'm going to go back to being empty is if I have the same number of B's as X's in my stack, but the number of X's in my stack is twice the number of A's that I read. And that kind of like transitively works out, right? So, for every B that I read, I'm going to pop. So I get 3 X's and then 2 X's and then 1 X, and then I'll be empty. So that's what I'm going to try to do. How am I actually going to do this? Well, here for every A that I read, I'm going to push 2x's. Remember, this is just a shorthand that you can use. So this is just a shorthand for something like, A, if you see Z naught, then you can do X, X, Z naught. And also A, if you see X, then you can do, oh boy, 3x's, right? So X, X, X. Right? Okay, so that's the shorthand for this. So I'm going to add 2x's for every A that I read. At some point, I'm going to guess that I'm done reading the A's, so I'm going to do an epsilon transition. And I'm going to start popping for, I'm going to start popping an X for every B that I read. Okay. And then I'm going to guess at some point that I'm done, right? And the only way that I can actually transition to the accept state is when I guess that I'm done, I actually have the stack being empty again. So I have Z naught at the top, or yeah, at the top of the stack. Okay. And this is going to be the PDA for A and B2. Okay, makes sense? Yeah, nice. Okay, cool. So now what about the other machine, right? Because this is a union of two languages. There was the other language, which was AMBN, where, M is greater or equal to N greater or equal to 0. So, yeah. Yeah, yeah, pop X from this time. Yeah, yeah, yeah. So for this other language, AMBN, it's also probably going to be something along the lines of the logic for ANBN, except that now, right, like ANBN is a subset of this language, right? Like it's fine because I have a greater or equal to, right? So if for every A, right, so if I have something like this, if for every A that I read, I push, then at some point I'm going to get 3x's, and then if for every B that I read, I'm going to pop, then at some point I'm going to get an empty stack. So that should still be good, right? That should still be accepted, right? But now the other thing that should be good is if I have an excess of x's, right? So if I do something like AAA and then BB, then, I'll have XXX at some point. And then at some point, I'll have something like just a single X on the stack, right? And that's also okay, right? So now you're going to think, well, does that mean that I have to hard code every single number of X's on the stack? Not really, right? Because as long as there's one X, it doesn't really matter what's below. It just means that I have at least one that's extra, right? So that's going to be the condition for me to transition. So let's just do that. For every A that I read, in this case, I'm going to push an X. I'm going to push an X, and then at some point, I'm going to have finished reading the A's. So I'm going to guess at that point that I should transition to popping. I'm going to go here. And then I can only transition to the accept state if, I'm done reading and my stack is empty, or I'm done reading and I have a surplus of x's, right? Okay. So this is going to be the machine M2, and this was the machine M1. So combining them together, you get the machine for L1 union L2. Okay, cool. Nice. Any questions about this? Yeah, yeah. No, right? I made sure that it wasn't, I think. Because here it's twice, right? Yeah, yeah. But good point, yeah. Okay, cool. Yeah, other questions? Yeah. Nice question. Okay. So uh, what happens if there's more B's than A's? Well, just a question mark. Nice. What happens given A, B, 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 for instance, right? Okay, well, let's see. Essentially, what's going to happen, like I'll just give you the immediate answer first, is the NPD is going to try every possible sort of execution, and it's going to jam every single place, so it's going to reject, right? But we can see this, right? Like at this point, the NPDA could either, guess to go here,
but then it would jam because there's Z naught on the stack. Oh, wait a minute. Oh, right. So remember, sorry, remember the condition for an NPDA to accept is, in this case, right, is has to finish reading the entire string. So acceptance by accept state is it has to finish reading the entire string. And it has to reach an accept state, right? So, you know, if it guesses to go here, but it hasn't consumed any input, then it jams, right? If maybe it consumes an A, so it pushes an X, then it jumps here, then it pops a B, so then the stack is back to being empty, so it can transition, but it hasn't read these last two, right? So again, that's a jam, right? And so whatever happens, you're going to jam either because you can't get here, or if you do get here, you haven't completely moved the pointer to the end of the string. Yeah, that's good. Yeah. Yeah, you can do that, but then your pointer is going to be here. So your pointer is going to be here, and you're going to be here. So to accept a string, you have to get to the accepted state, and your pointer has to be here. You have, uh, no, I'm going to let you think for why that's not true, because I have to move on, but think about it. Think about why that's not the case. No. Okay, let's maybe take it offline, because we have to move on. Okay, so this was for the question from the lecture. Let's do a question which is actually from the problem set. So I don't even know what the question number is. No. So some question number on the problem set that's about designing PDAs for languages. It's question C, and the language in this case is A2N B3N, for n greater or equal to 0. Okay, so I'm going to give you, let's say, 4 minutes to think about it. Well, not 4 seconds. Okay, so think about it. And let's see, maybe. It's for that. Your then. Well, push one with the side here, change my problem, and then it's exact, I waited, I had one video, I used it and then I. Yeah, but, no, you can't, you don't have to use something. Well, you can't just really look at it. And then what does this mean? So why would that some people say, X's? No, it doesn't, right? Like the number of X's that you can. This is just to ensure that the top of the stack is X or the top of the stack is Y, right? Yeah. So like, there's like the epsilon here actually is the same as the epsilon in that base. So it's like if you're reading a unit and now you're using point of here and here, then you can just jump and you point of it. You say like this, but now you can also probably catch. It's necessary because we want to ensure that you have either the same number of used or an extra number of holes.
So the A's are pushing.
And this is nothing.
Yeah.
Yes. Okay, makes sense. And the only condition you have is that entities, they will follow the pattern.
Next. Good.
Yeah.
It's good.
Yeah, but I.
Okay. Yeah. Yeah. Like you want the delta, the increase delta. Yeah. Otherwise, you can't do, what's on, yes, yeah. Like this, the left here has to be a simple. Right. Okay. So one thing that you have to remember is the input type or delta, right, in the PDA is um, Q by sigma by gamma gives you Q by gamma star, right? So you're only allowed to pop a single letter from the top of the stack. So this is something that is kind of important if the strategy that you try to do is something like, push push three X's and then try to pop two X's, something like that. So instead, I mean, what we'll do is kind of the similar general idea. So let's start with the observation that, something like A2N, B3N. So A2N, B3N, this is kind of like, well, it's not kind of like, it's exactly like A square, so AA and then N, and then B cube and then N, right? So what you would like to kind of do is for every pair of A's that you see, you push an X. And then for every triple of B's that you see, you pop an X, right? So that's kind of what we're going to do essentially. So that'll work because if I have something like AA, BBB, and then BBB, right? Then, if for every pair of A, I push, right? Then at this point, I'll have two X's. And then if for every triple of B's I pop, then, here I'll have a single X, and then here I'll be N, right? And so this kind of ensures that I have sort of A2N, B2N, right? Because this is kind of like for N is equal to 2, okay? So now the question is just like, how do I do this? Well, I just sort of introduce sort of cycles in my PDA, right? So I'll start with the cycle for pushing X for every AA. So this is going to be a two-state cycle. So for the first A you see, you're going to push an X. And then for the second A you see, you're just going to transition back, right? So for this first A, right, for this first A, I push an X, and then I just transition back. Okay. Then again, for this second pair, for this first X, I push, and then I transition back. Okay. Then at some point, I'm going to be done with this, and I'll guess, right, I'll guess that I have to move on. to sort of the 3 cycle, right? So here I'm going to pop x for every b, right? And how is this going to look like? Well, for the first b that I read, I'm going to pop an x, right? And then for the other 2 b's, I'm just going to transition back, right? So for this one, I'll transition back. Well, this one I'll use to transition back, right? And then at this point, right, I only accept if at some point, like I'm done reading, right? So I can use my epsilon transition, and my stack is back to being empty, right? So let's assume Z naught at the bottom of the stack, right? And then I go to a next option. Okay, and that's how that works. Cool, makes sense? Yeah. Are both, sorry? I don't think it works because of this restriction. Like you can't do something like B and then XX. This is not an allowed transition.
Oh.
Yeah. That's a good question though. Okay, cool. All right. So we'll do one last one and then I think we can wrap up. This one will be question D. Again, I actually don't know the question number. Where here the language is W in A comma B comma C whole star. So the alphabet is 3 letters, where the number of A's plus the number of B's is different from the number of C's. Okay, so this is kind of like the complement of the previous language, right? Because in the previous language, or like some time back, right? Because in the previous language we had this equality. Now we want an inequality, right? Something that would be in the language, let's call this L, is A, B, and then C. Yeah, this is an L, right? Because I have NA plus NB, that's 2, and NC is 1. But something like A, B, C, C, this is not an L, right? So to do this, again, I'm going to use the same kind of idea. I'm going to start with a simpler language, because otherwise it's a bit too complicated to immediately jump into the solution for this one. So the simpler language, let's start with the simpler language. So the simpler language is going to be L prime, where W is in A comma B star, and NA is equal to NB, right? So we're going to start with, I have 2 letters, and I actually want an equality. And then we're going to see how we can work to the inequality with 3 letters. Okay. So how is this going to work? With a stack, right? Because remember, we need to design an NPDA. Essentially, the trick here is to make the stack represent NA minus NB, right? That's essentially going to be the idea, right? So, and what I'm going to do is I'm going to use, because like I can have either a positive or a negative, I'm going to use 2 types of symbols. So if I have something like 4 x's, right? Then this is like NA minus NB is equal to plus 4, right? And if I have something like, I don't know, 2 y's, then that's NA minus NB is equal to like minus 2. And this is going to be the idea, right? And the idea is that, you know, at the end, so if I have something like AA, BA, BB, then, you know, what's going to happen if I go through this string, which is in L prime, then I'll get something like, you know, I'll start with an empty stack, then I'll get X, then I'll get XX. Then if I see a B, right, if I see a B and I have an X, then I just have to take it off, right? So I like decrement, right? So I just have a single X, then I have an A, so I add back the X, and I have 2 more B's, so I'm going to decrement, right? So I'm going to empty, okay?
And let's just, for the purposes of illustration, suppose I have an extra b, right? So now I have an extra b and an a. Well, now at this point, I have to make my stack negative. So I'll make it negative. And then I'll read this a, seeing this y, I'll pop it, right? So then I'll be back to here. Okay, so this is the general pattern that I'm going to use. Okay, and the accepting condition is that, you know, at the end, my stack only has a null, right? So now, how do I actually do this, right? Because like it's nice to sort of show you pictorially, but what is the state transition diagram going to look like? It's only going to actually require two states, and it would only need to require one, I think, if you did by an empty stack, but I'm not sure, don't quote me. So I'm going to transition to the accept state if my stack is empty, right? Because of the sort of condition that I told you about. Now, what's going to be the transitions for this state? Well, it has to be a self loop, right? And what's going to happen is, let's do the transitions for when I read an A. So if I read an A and I have a Z naught, right, then that means that I should add, right? I should like increment my counter to +1. +1 is like I have X on my stack, right? So that should be X Z naught. If I have an A and there's an X at the top of my stack, then I should add an additional X. So I'll get XX. If I have an A and there's a Y at the top of my stack, what should I do with it? Pop it, yes, very good. And it's sort of the symmetric thing, but for B, right? So if I read B's, then I'll have three transitions. For Z naught, I'll add Y. For Y, I'll add an extra Y. And for X, I'll pop it, right? And so you can kind of see that this kind of does what I described here, right? So, you know, I'm here, I read an A, so I use this, I add an X. I'm here, I use this transition, I add an extra X. I'm here, I use this transition, I pop an X. Uh, I'm here, right? I use this transition, I add an extra X and so on, right? So this kind of ensures that when I transition, it's either because I'm at some substring where that substring has the same number of A's and B's, or I'm done and I have the same number of A's and B's, right? So this is going to be the NPDA for L prime, right? Now, who can try to tell me how I could do still a simplified language, but NA different from NB? Yeah. So what? Yeah. Yes. Yeah, absolutely. Very good. Excellent. So the accepting condition is no longer that the stack has to be empty. It has to be that it has an excess of either X's or Y's, right? Very nice. So I'll replace this with epsilon X gives you X, epsilon Y gives you Y. Okay. So again, this is still the simplified language L double prime. If we actually go back to our language L, which is A, B, C star, where, what did I say it was? NA plus NB is different from NC. Okay. So now let me give you 2 minutes to try to apply this logic. Okay. So hopefully it shouldn't be too bad. There's something that actually proves yeah, it doesn't matter. Yeah, it doesn't matter for people. Yeah. But you can try to think of a why if you want. There's like a reason, because you can actually get equal if you do this, and you can push when you have like a y, and you should be like problem. Yeah. Yeah. Okay. I think the thing hasn't rung, but I give you an extra minute, but I think everyone's done. So, okay, I'll just do it. Okay. I know people are dying to go out in the rain. Is it still rain? It's not raining. Nice. Okay, so how do I generalize this to this language L? Essentially, it's kind of like the same idea as before. I just want to kind of treat two of the letters the same, right? In this case, I need to sort of change this for the C's, right? Right, so my stack is going to represent NA plus NB minus NC, right? So then I'll have these transitions plus extra transitions for the B's being exactly the same as the A's because I'm treating them as if they were also B's, right? So I just have to replace this with B. There was a nice solution which tried to kind of do this a bit more efficiently by only doing something like a yeah, so A or B. I'll just write A or B. Simple. So this is just not standard notation, so don't do this in there. But like I'm just to simplify. Uh, on Y. Okay, and then this. But this is what you had before, right? Okay, I'm gonna assume I understand. This is what you had before, right? Something like this? Yeah, something like this. Okay, so this is a good attempt. I commend the efficiency of the transitions. This doesn't quite work because you can get a situation where you have something like X and then Y, and then actually it's like they cancel out, so you have the same number of A's and B's, but to the NPDA, it seems like it should transition, and so it accepts. So you get a false positive, okay? So it actually didn't matter if you wanted equality, because like this still is equality, but it does matter if you want a surplus, right? So this doesn't work for inequality. But it's nice that that was a question. Doesn't work for inequality. Okay, that's about it. Somehow we managed to finish before 25. So yeah, next week we'll do more exercises on CNF, CYK, and then maybe I'll try to do a pumping lemma question. Okay, thanks a lot. Have a nice weekend.